Good morning, everyone. Let me first of all thank the organizers for the opportunity to speak here in Tsukuba. Maybe you have already noticed that this is the place where I'm currently living, so this is my home, so it's a pleasure to be here and to talk to you about the recent work that we've been doing on silicon spintronics. This is not work that is performed in my current location, which is the National Institute of Advanced Industrial Science and Technology, AIST, particularly the Spintronics Research Center. But what I will be talking about today is the work that I've been doing together with this group of PhD students and postdocs over the last few years on silicon spintronics. Now, why are we interested in implementing spin functionality into silicon? It's often stated that silicon is an attractive material for spintronics because of the fact that the spin degree of freedom is only weakly coupled to other degrees of freedom in the material. This is because the spin-orbit interaction is relatively low. It's a low mass material. Also, the crystal has inversion symmetry, which removes one of the main spin relaxation mechanisms like the Akhonov-Borel. And also most of the silicon isotopes don't have nuclear spin, so also spin relaxation via nuclear hyperfine interactions is relatively weak. However, this is true. I think that the most important reason why silicon is attractive is because it's the mainstream semiconductor. It's a semiconductor that dominates the world of semiconductors. And therefore there is a huge technology base that we can and maybe we should be making use of. Now, the same can be said for ferromagnetic materials like iron, nickel, and cobalt. These are widely used in magnetic data storage and magnetic recording, and there's also a huge technology base for these materials. So what we would actually like to do is to combine these two types of technologies, ferromagnetic technologies and semiconductor technologies, and make use of the unique properties of these two types of materials. These unique properties for ferromagnets are stable memory functionality. These materials have hysteresis. You can switch them very fast on nanosecond or even recently shown femtosecond timescales. And these magnetic materials have high ordering temperature, so they operate at room temperature. Excuse me. On the other hand, semiconductors, you can do band gap engineering, so you can make all kinds of low-dimensional quantum well and quantum dot structures. You can control the carrier density and type from n-type to p-type, and maybe more important is that you can electrically gate these materials and thereby change the properties. So what we in the end would like to do is to combine the unique properties of ferromagnetic and semiconductor materials and create something new, something extra, or something better. At least that's the goal. Now what this field is concerned with in general is, from a technology point of view, the question whether we can create spin-based transistors, switches, and logic circuits, and characterize what their performance is and whether they are actually better or different than the structures that we already have. And from a more science point of view, the question is, how do we create spin polarization in semiconductors? How does it propagate through structures and interfaces, and how do we actually control and manipulate the spin polarization? So what I'm going to do today is first describe to you a milestone achievement, that is the creation of spin polarization in silicon at room temperature. And I'll describe to you how we do that and what the basic characteristics are. And in the second part of the presentation, I will talk about how the spins in a non-magnetic material behave near an interface with a ferromagnetic material. And it turns out that the spin polarization and the spin dynamics of spins near a ferromagnetic interface are very much influenced by the presence of the ferromagnetic material. So that's the second part. So let's start with creating spin polarization in silicon at room temperature. What we are going to make use of is spin polarized tunneling. So the fact that tunneling from a ferromagnetic material across an oxide tunnel barrier is highly spin dependent. So if we create a structure on top of silicon consisting of a very thin oxide tunnel barrier and a ferromagnetic electrode, and we drive a tunnel current through the structure, we preferentially inject one type of spin, let's say the majority spin, from the ferromagnet into the semiconductor. This raises the electrochemical potential for that particular spin compared to the electrochemical potential of the other spin, and therefore we create a spin accumulation. So the spin accumulation denoted by delta mu, the difference in the electrochemical potential between the two spins. In simple theory, the magnitude of the spin accumulation is given by the rate with which you inject spin polarized electrons into the silicon and the balance of that with spin relaxation, which tends to reduce the spin accumulation in the semiconductor to zero. The balance of these two processes determines, at least in simple models, the magnitude of delta mu. What we're going to do in our experiment is also manipulate the spins with an external magnetic field. This is known as the Handler effect. So basically, if you have spins that are polarized in the plane of the structure, so if you have a ferromagnet which has in-plane magnetization, you transfer spins into the non-magnetic material also with in-plane spin orientation. If you then apply a small magnetic field perpendicular to the spins will start to precess about that magnetic field. And as a result of that, the spin accumulation decays with increasing magnetic field. And typically you observe something like a Handler type of Lorentzian line shape where the spin accumulation at zero magnetic field is maximum, but it gradually decreases when you increase the magnetic field and you increase the precession frequency. From such measurements you can extract the magnitude of the spin accumulation from the peak amplitude, but in principle you can also extract the spin lifetime because it's inversely proportional to the width of this Handler curve. Let me tell you a few things about the device fabrication. We start normally with commercial silicon wafers and define a contact by first growing a thick thermal oxide and then etching with HF a contact hole to define the area. And then we deposit aluminum oxide tunnel barrier from an aluminum oxide single crystal by E-beam evaporation, and then following the deposition of the ferromagnetic electrode. However, we introduced another step here, that is in situ plasma oxidation of the aluminum oxide to enhance the oxygen content of the tunnel barriers. We also found that that process also oxidizes the silicon underneath the aluminum oxide a little bit, which you can see by comparing the real thickness of the tunnel barrier that you can observe in TEM cross sections with the actual nominal thickness of aluminum oxide that was deposited. And we find that the actual thickness of the tunnel barrier is always a little bit higher than that of the amount of aluminum oxide that was deposited. So that's due to the under-oxidation of the silicon forming silicon oxide. So let's show the first room temperature data on spin polarization in silicon. So here's the data. This is the voltage signal as a function of the external magnetic field perpendicular to the injected spins, and you indeed see this nice Lorentzian type of line shape that we were expecting. So at zero magnetic field we have a static spin polarization, there's no precession, but if we increase the magnetic field we see that the spin polarization gradually reduces to zero with the characteristic Lorentzian line shape. This was done for silicon, aluminum oxide, nickel iron structures at room temperature, with the silicon having a doping concentration in the 10 to the 19th per centimeter cubed range. The measurement was done in the so-called three-terminal geometry, where we inject spins from this ferromagnet into the silicon using this current contacts and measure the resulting voltage across the tunnel junction by this pair of contacts. And what that measurement does is it uses the same ferromagnet for injection of the spins as well as detection of the spins. So there's no lateral transport through the silicon in this case. It uses the same one ferromagnetic contact for injection as well as detection. But this measurement demonstrates that we're able to inject spin polarization into silicon, that we're able to detect the spin polarization, but also that we're able to manipulate the spin polarization with an external magnetic field and create a coherent precession. Let's say one thing about how we detect the spin polarization. Basically, the tunnel resistance or the voltage drop over a tunnel barrier at constant current depends on the magnitude of the spin accumulation. You can relatively easily show that by writing down the equations for the tunnel current for the two different spin orientations. They're proportional to the tunnel conductance times a potential difference, which is different for the two different spins when you have a non-zero delta mu. If you worked out the equations, then you can easily see that if you change the magnitude of delta mu from some finite value to 0, which is what we do with the Handler effect, that in that case the total tunnel current changes. Or if you keep the tunnel current constant, you will see that the voltage drop over this junction changes, and you can write down an equation for that. The voltage drop is equal to half the spin accumulation times the polarization of the tunnel conductance. We know for our nickel, iron, aluminum oxide structures that that's about 30%. So what we can now do is, from the measured voltage signal, compute what the spin accumulation is, and that's about 1.2 millielectron volt. The other thing you can do is to extract from the width of this Handler curve the lifetime, which comes out to be about 142 picosecond, and in principle the spin lifetime is about 142 picosecond, but I have written here a larger than sign. I will explain in the second part of my talk why there is not an equal sign but a larger than sign. For the moment, this is the spin lifetime in silicon. It's very important when you do such experiments to do a control experiment to convince yourself that you're not measuring some kind of artifact. So the experiment that we did was to introduce between the tunnel barrier and the ferromagnetic electrode a very thin layer of a non-magnetic material, a few nanometers, which is sufficient to remove the spin polarization of the tunnel current. So we inject unpolarized electrons into the silicon, and we expect that the signal in that case disappears. However, if the signal that we measure here would have been due to artifacts, for example due to AMR type of effects in the ferromagnets, or to fringe fields that the ferromagnet produce and affect the current in the silicon, all of those artifacts should still be there because the ferromagnet is still there, the current is still running the same way. However, we see that the signal nicely disappears as we expect. So this is a proof that the signal that we measure is really due to spin polarized tunneling into the semiconductor. Now we can now investigate a number of characteristic features, and one of the important features is how the signal, the spin accumulation, depends on the current, direction and density. And we can either operate the structure under spin injection, meaning electrons injected from the ferromagnet into the semiconductor, and you see that for that current polarity the magnitude of the spin accumulation scales linearly with the current density as is expected. However, we see that if we go to the opposite bias polarity, which corresponds to the extraction of spin polarized electrons, so we extract one spin preferentially, obviously that also polarizes the remaining spins in the semiconductor, so we do get a non-zero spin accumulation also for this polarity, but it deviates from the linear behavior. This is something that we frequently see, and at this moment we don't understand this very well. One thing I should point out is that this is a nice feature that the spin accumulation scales with the current density. The values that we obtain at the moment is about 3 millielectron volt, and I should note that the value, these type of values are at least 2 or 3 orders of magnitude larger than what you would expect on the basis of the standard theory that is available for these devices. We realized this when we did these experiments, and we also realized that there is a proposal from Tranadal in this paper which can lead to an enhancement of the spin accumulation that you measure in such structures. That enhancement occurs when you have interface states, and tunneling through these structures is by 2 steps. So if you have interface states at the semiconductor oxide interface that are separated from the bulk bands of the semiconductor by a Schottky barrier, then the tunnel current can actually go in 2 steps. In that case, the spin accumulation that you create in the interface states is much larger than the spin accumulation in the bulk bands. And so the question was, is this the reason why we observe such large effects? It should be noted that this enhancement only occurs when the interface states are separated from the bulk bands with a sufficiently large barrier. However, if there's no Schottky barrier, or if there's a low resistance Schottky barrier, the electrical contact between the interface states and the bulk bands is very good, and in that case you cannot have a different spin accumulation in the bulk bands and the interface states. So what we decided to do is a test experiment with a technique that we developed earlier using cesium. And we know, and you can look up in this reference the details, that if we treat the silicon surface with a little bit of cesium submonolayer before preparing the tunnel barrier, that the Schottky barrier is greatly reduced. So basically what we're going to do, without the cesium, we have a Schottky barrier here, and the question is, if we have interface states here, do we have two-step tunneling and some enhancement of the spin accumulation, yes or no? And if we do have this enhancement, and we then remove the Schottky barrier, then we expect a large drop in the signal by several orders of magnitude. What we observe in our experiments is basically not much of a change, certainly not at room temperature. So this is the spin signal here as a function of temperature for devices without cesium and with the cesium treatment, and you see at room temperature there's only very little difference in the magnitude of the signal, and you also see that the spin lifetime is almost the same with and without cesium. So basically the conclusion is the two-step tunneling mechanism is not active in our devices. So we really are sure that the large spin polarization exists in the bulk of the silicon bands. That same conclusion can be arrived at with some more recent data using spin LEDs, which we did together with Barry Yonka's group at NRL. So those are, in that case, we inject spin polarized electrons from iron into a silicon light emitting diode structure and detect the spin polarization using luminescence. And from analysis of these structures, we know that the luminescence comes from at least 300 nanometers away from the injection interface. And yet we see a nice circular polarization, and the polarization scales with the magnetization of the ferromagnetic electrode. So this experiment also tells you that we're able to create a highly spin polarized electrons in the semiconductor bulk bands well away from the injection interface. Can we do the same in p-type material? That's another question we addressed. In that case, the carriers are in the valence band of the semiconductor. The carriers are holes, and the question is, can we, by spin polarized tunneling from a ferromagnet to the valence band, also introduce a spin polarization of the holes? And in principle, this should work. And of course it does, otherwise I wouldn't have shown this. So this is similar type of Hanle data for p-type silicon, aluminum oxide contact, nickel iron ferromagnet at room temperature. You see for both positive as well as negative current a nice Hanle signal with a Lorentzian type of line shape, and this shows that we can also inject spin polarized holes into the valence band of p-type silicon. We can detect the spin polarization of the holes, and we can also make the holes precess in the transverse magnetic field. This was done for a doping concentration of about 5 × 10⁻18. Okay, the remaining time I will spend on looking at spin precession near an interface with a ferromagnet. Is that indicating the remaining time including discussion?
Presentation.
Okay, okay. So the second part of the talk I will focus on how spin precession and spin polarization is affected by the presence of an interface with a ferromagnet. And there are different mechanisms that you can think of, but the mechanism that I'm going to be focusing on is direct magnetostatic interaction from the ferromagnet to the semiconductor, which occurs when the ferromagnetic interface is not perfectly smooth. And the first indication that this is actually an important factor comes from the fact that the Hanle line width that we observe in our structures depends on the type of ferromagnetic electrode that we use. So for iron, for example, the line width is much broader than for nickel iron, which means, or would seem to mean, that the spin lifetime in the semiconductor is reduced. Typically, the spin lifetime or the Hanle line width in a non-magnetic semiconductor is determined by parameters of the semiconductor, the spin lifetime and the G factor. However, we see that the line width depends on the ferromagnetic electrode. Also note that the line width increases systematically when the magnetization of the ferromagnet is increased from nickel iron to cobalt to iron. Now, the way to understand this is to realize that if you have a ferromagnetic surface which is not perfectly smooth, you have some local magnetostatic fields that penetrate into the semiconductor. These local magnetostatic fields are inhomogeneous, both in magnitude and in direction, and that means that the spins in the semiconductor feel these local magnetostatic fields, and they will have different precession frequency and different axes of precession depending on where the spins are. And to prove that this is the correct mechanism, we did an experiment with an in-plane magnetic field and observed something that we will refer to as the inverted Handler effect. So this shows the spin signal, the normal Handler signal, reduction of the spin signal with external magnetic field. This is the signal that we observe when we apply an in-plane magnetic field. We see actually an enhancement of the spin signal as a function of the magnetic field. And the way to understand this is that at zero external magnetic field, the spin accumulation is already reduced because the spins are precessing in the local magnetostatic fields produced by the roughness. So this precession causes a reduction of the spin accumulation even without an external field. If you now add an in-plane magnetic field along the direction of the spins, then the spins will precess in the vector sum of these two magnetic fields. If you make the in-plane magnetic field large enough, that vector sum rotates into the direction of the spin and the precession disappears. And this is indeed why the signal is enhanced by an in-plane magnetic field. We see this in inverted Handler signal for all our devices with different ferromagnetic electrodes. This is data for p-type. And you also see that the width of this inverted Handler signal increases systematically when you go to ferromagnets with a higher magnetization. The same thing we observe for n-type silicon. You can describe this. Am I out of time now? The screen has disappeared. I have a few more minutes. Okay, thank you. You can describe this by including in the expression for the spin dynamics in the spin precession term an arbitrary magnetic field, omega, which has x, y, and z components, and that consists of a homogeneous external magnetic field plus local magnetostatic fields that have x, y, and z components and also are spatially varying. You can solve these equations relatively easy. This is just precession of a spin along an arbitrary oriented magnetic field. An interesting point to note here is that all of these spin components that you get have a Lorentzian type of line shape, but also a constant contribution. And a second important point is that this calculation was done assuming that the spins that are injected are perfectly aligned with the ferromagnetic magnetization in the x direction. And yet the steady state spin polarization that develops has non-zero y and z components, which means that the spin polarization that is created is non-collinear with the magnetization of the ferromagnet. Now the task is to find reasonable values of these magnetostatic fields. We did the simplest we could think of, just approximate a rough ferromagnetic surface with an array of magnetic dipoles. You can then relatively easily calculate the magnetostatic field patterns, x, y, and z components, and how it spatially varies. And for each point in space, you can now take the x, y, and z component, put it in the equation I just showed you, and calculate the spin accumulation. And this is the result we obtain. So at zero external magnetic field, we see that as a function of the lateral position, there's inhomogeneity in the spin accumulation. You have regions in blue where the spin accumulation is suppressed to almost zero, and regions in red where the spin accumulation has hardly any effect. What you can now also do is do these calculations as a function of external magnetic field in the z direction, which suppresses the spin accumulation everywhere, or with an in-plane magnetic field, which shows you a recovery of the spin signal everywhere due to what I refer to as the inverted Handler effect. Now the next thing you can do is to average the spin signal over the xy plane and calculate what the resulting Handler curves would be for two different strengths of the dipole fields, which represent different strength of the magnetization of the ferromagnet. And for example, if you have a strong magnetostatic fields, you see three things. One is a reduction of the spin polarization at zero external magnetic field. You see the inverted Handle effect appearing. But maybe the most important thing is that these calculations were done with a spin lifetime of 1 nanosecond. And yet the Handle signal that you observe in this case is much broader than what you would expect for a Lorentzian with 1 nanosecond. That means that this mechanism leads to an apparent increase of the spin lifetime. And that's also the reason why I included a larger than sign in the beginning of my talk. So the final point is that by making structures with different ferromagnetic materials, for example with nickel on N-type, we observe that the Handle line width is much more narrow, and we observe a new lower limit of the spin lifetime in silicon at room temperature of 285 degrees. And I think we can improve this value even more by reducing these magnetostatic fields. So let me conclude that silicon spintronics has reached room temperature, but there's also many opportunities still, both for physics and materials, and also for device engineering and technology. Thank you for your attention.